Right. Gemma Kentish, thank you for listening. Well, I do. I have done. I've listened to you. All right? First of all, I have to listen to, let's just go 2 minutes and 8 seconds. Yeah? So, I don't know how many times I've clicked on this. I don't know how many hours in aggregated time it takes to play this little jingle. All right? But, you know, you can tell the sort of state of mind I'm in having listened to it about a dozen times. You've got some content in here, right? Let's just go through. You can see the content at the bottom emerging. I'm going to chew a certain amount of time by going through what you say and how I would say it. And I know I'm going to chew some time here, but I think you at Chemistry SKE, and Gemma Kentish in particular, might like to think about how much wasted time there is in this video and how much time is actually being spent saying things that aren't being said particularly cleverly. So let's go through it one step at a time. I'll try to keep my temper under control.
So we've looked at some energy profile diagrams, but we haven't actually mentioned activation energy or shown these on our profile diagrams yet.
Right, now why is that then? Alright, how many of these activation energy diagrams have you scratched on a board, put on a whiteboard, asked a student to produce, and you haven't yet mentioned activation energy? Now this is a graph. This activation energy peak is shown on a graph. Click play to find out what this is. Well, I think you are really playing about here. All right? You're not actually saying, why is this diagram so useful?
So at Key Stage 4, students will be 100% aware of the fact that reactants need a certain amount of energy for a reaction to proceed. And it's
right, will they? Will they honestly? At Key Stage 4, they need to be aware that a certain amount of activation energy is required. Now, you've got no symbols on the chart here saying what the amount of this is, this quantitative amount. Right, how high this is relative to this. I appreciate, well, for a start, we got energy on this side, right? Rather than enthalpy. So is this a Key Stage 4 diagram or is this an A-level diagram? It's in the middle of the A-level pack of educational resources, but it is labelled energy rather than enthalpy. I thought the whole point was that at A-level we called this enthalpy. Time. No marks here along the bottom to say, you know, 1 minute, 2 minutes, 10 to the 16 minutes, 10 to the 16 nanoseconds, or anything like that. But we'll carry on and I'll listen to you for another few minutes and then I'll see what I have to say about what the next thing you say.
called the activation energy. Now in year 12 we start to use this notation here, so E with the subscript A stands for.
Okay, in year 12, activation energy is introduced. No, it's introduced at a different key stage, but we don't introduce a simple notation, which is, let's use the word E for energy and the subscript A for activation. I mean, it's not particularly complicated. It doesn't mean multiply E by A and all that stuff. I've gone over that at great length in this assessment of your learning materials.
Situation energy. So, again, reactants shown on
Okay, so you just told me it's an enthalpy, you little...
Now, in order for a reaction to take place, the bonds within the
So you just told me it's an enthalpy diagram and you've put energy up here. Still. There was a you know, a little tiny moment where you had it right. Ah, God oh bloody mighty, this is like where the hell are we in this diagram? Let's reduce this out of full screen for a start and get it onto a... Right, it still doesn't... I'll try and pause it.
Still situation energy. So...
Enthalpy profile diagram. Enthalpy profile diagram with energy labelled up the side. Well, there's a mark off for that then, alright?
Again, reactants shown on the very left-hand side of the profile diagram.
Yeah, now what does that mean? That means that the reactants exist for a period of time at a constant enthalpy until the reaction starts.
Now, in order...
And then it climbs to a transition state. Now listen very carefully to what you say to yourself, or what you say to the students now.
For a reaction to take place, the bonds within the reactant molecules need to be broken. So breaking bonds is an end.
Right. First of all, for the reaction to start, or even to proceed, yes, I agree that some bonds need to be broken. Do they all need to be broken? No, the reaction can start with just breaking a few bonds. But symbolically, what we're doing is we are saying this would be the theoretical enthalpy of all of the reactions if they were all broken simultaneously, or rather more at the A point of time here, or the I point of time, this point here, if they were all broken at that point in time, then one can conceptualize these reactants as existing in a transition state. Doesn't necessarily mean that the reactions are all in the transition state. Some of them might be, some of them might still be reactants, some of them by this stage may already have produced products. So, what does it say in terms of the words? In order for a reaction to take place, the bonds within the reactant molecules need to be broken. For a reaction to take place, no, for the entire reaction to take place, all the bonds within the reactant molecules need to be broken. That's not true. Some bonds within the reactant molecules need to be broken. That's true. Some bonds within some of the reactant molecules need to be broken. That's even more true. The transition state is a theoretical state in which all of the bonds that are going to be broken and remade are broken. And I understand that we can't do this on a three-dimensional graph or something like that, or that it would introduce too much complexity for it to be on a three-dimensional graph. What is this? Somebody's interrupting me while I'm making a video. That's bloody annoying. Right. Anyway, the point of highest energy, part way between the reactants and the products, is the transition state. I'll argue that point with you in a minute.
Endothermic process. Okay, so we are going to need to provide some energy for those bonds to be broken. So once we've got all of the atoms with their bonds broken, we'll call this the transition state, okay?
No. Once we have not got all of the atoms, have we got the transition state? You don't reduce everything to atoms in order to reassemble them in a chemical reaction. Some bonds are broken in order that they are reassembled. It's terrible what you're telling them.
So this is a very, very short-lived state. You won't be able to isolate these individual atoms, okay?
Again, it's not your individual atoms. Okay? Granted, you cannot isolate them. Granted, it is short-lived. But no, it is not a state of atoms.
But what will happen once they've reached that is that they're going to form new bonds. So bond making is an exothermic process. Okay, so we are going to release energy.
Right. Are you going to release energy in an endothermic reaction? The bonds are still broken. The bonds are still going to form again, but they aren't necessarily going to give out energy every time. How does this look for an endothermic reaction? Products here should be up here. In a minute, you do a silly thing where you say, and when you got a catalyst, they'll come from here down to here. Well, actually, if this is 10 to the 1000 years and this is 10 to the 0 seconds, these reactants with a catalyst could be down here as these reactants could form some products, and the timeline here could be incredibly short. Catalyst doesn't, well, it's not just you. Every chemist who ever teaches this stuff never teaches it in this.
So our products in this case have ended up lower. So what that is telling us...
Well, our products have ended up lower. No, our products have ended up possibly in the atmosphere, possibly in a test tube, possibly in some gunk or whatever that's left in the bottom of some reaction vessel or whatever. That's where the products have ended up. The energy state of the product is ended up here. That is maybe what you're telling people. But you're not telling them the products have ended up here. Here is some kind of not physical space, but a conceptual space in which entropy, and you still haven't labelled this diagram enthalpy, my mistake there, sorry. I'm getting tiswas up. Enthalpy is up here, and the product enthalpy state at this level, at this end of the reaction, is somewhere on the timeline. Not only is it somewhere on the timeline, but it's somewhere on the enthalpy level. But my frustration here is not with you personally, it's with myself for not properly understanding it or being able to communicate it.
Endothermic bond breaking, okay?
Endothermic bond breaking. Can't fault that. When new bonds are made and the products are formed, energy is released. You're describing the ascent on this line and the descent on this line. You're not describing the ultimate level at which the products end up. So this ascent is a bond breaking, and this descent, whether it descends to this point or this point lower, that is when the bonds are forming. When new bonds are made and the products are formed, energy is released. No, I don't know that that's necessarily true. Because if the products are higher in enthalpy than the reactants, still goes through a transition state quite conceivably, though, yes, I have to think about that one a little bit more, but let's ignore that. We'll carry on.
Is required less energy than the overall energy that's been released, so we get an exothermic reaction.
Well, we may get an exothermic reaction, but you're not telling me that all reactions are exothermic, are you? Because we've spent the entire course and all of year key stage 3, key stage 4 learning that there's certain things called endothermic reactions, and we've... No, it's too simplistic.
So the activation energy is measured from the reactant lines to the very top of the transition.
Right, is it? I mean, obviously, it's a definition, all right? It's a concept that there is some activation energy, but if you've got a mole of hydrogen and a mole and half a mole of oxygen, you've got hydrogen reacting with oxygen, okay? They go through a transition state. But the moment you start that reaction off, bang, 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 every single atom in that is going to react in sequence. Now, the transition state refers to a hypothetical state in which you can plot what the value might be of all of the mole of hydrogen and the half a mole of oxygen come on, stay with it. It's a hypothetical state, and it by no means means that, like, the reactants all go to the transition state, hang around there for a millisecond, and then drop off down here into products. Reactants and products are being formed products are being formed from reactants all the time in a one-way reaction. We aren't even starting to talk about multiple reversible reactions or equilibria yet. The activation energy of each reaction is different. I'll agree with you there.
States. So the activation energy of every reaction is different, and we can show how...
Actually, the activation energy of some reactions could quite conceivably be the same because they just happen to be the same. I mean, it's a mathematical number. It doesn't mean to say that they're all different, but you get, okay, that's a really pedantic point on mine.
Activation energy changes with the use of the catalyst. So we would start at the same level here, and our line or...
Right, so if you're drawing another line on the graph, why not draw it on the graph? Okay, what you're telling me is that the activation energy is not so high with a catalyst. I think that what you're telling me is that a catalyst does not activate all of the reactants in one go. It activates a few, and then a few more, and then a few more, and then a few more, and as the products arise, the activation sites on the catalyst become filled and unfilled. But you don't even start to try and
curve just be lower, it would end up back at the same level as the...
Yes, it would just be lower, but it would end up at the same point. No, it wouldn't. It would end up at the same level, but possibly months or years or decades ahead of where it might be if you didn't have a catalyst. Right, so now we got the remainder, and thank you for listening.